Okay. All right, so today we'll be looking at some applications, and I think you'll find this very interesting because we get to do some actual examples of how these concepts can be used in the real world. And a lot of these you're probably already familiar with to a certain degree. We want to focus our attention right now on exponential growth and decay models. So now, just as a quick review, an exponential function is one which involves e to the x power. And if you look at a graph on Symbolab, let's just quickly run through a couple so you can see what I mean. Let's try for our first function, something simple like y equals e to the x. Okay, so we'll take a look at that. And you'll notice what's happening here is that the graph increases very slowly for the longest time. And then all of a sudden, once we move into the first quadrant, it really increases very, very quickly. Okay, so in other words, we say that the growth is exponential because this is e to the x. And so anything that behaves like this will start to grow very slowly initially, and then it will start growing very, very rapidly as time evolves. Now, on the other hand, if we look at, let's say, y equals e to the minus x, let's try that one. We have just the opposite situation. So in other words, the graph is falling off very, very quickly. Whatever this variable is, it's falling off very quickly. And so what we're seeing here is rather than economic growth, we call this economic decay, which means that whatever this variable is, it is falling off very, very quickly, although eventually the decline starts to decelerate a little, but it is falling at a very rapid rate. So we're going to be looking at applications of these two basic functions. And so exponential growth appears in several applications. For one thing, the growth of a population may have or experience exponential growth. In particular, you may remember from high school biology that bacteria tend to grow this way. Once they get started, they grow very, very quickly. Also, if you are investing funds, let's say into a stock or a bond or a savings account, it's possible too that the growth in your investment will experience exponential growth. And so we'll see an example of that in a few minutes. But as far as the decay is concerned, the one example you almost certainly were introduced to in high school physics was the half-life of a radioactive element, which means that the amount of radioactive material in the element declines very, very rapidly. And we introduced the concept of half-life and also carbon dating, which is so famous. Every show you've ever seen on TV where, we're trying to figure out how old something is. Often it is dated with carbon dating, and that's because the decay rate of the carbon-14 isotope is very well understood. So it's possible to figure out how old something is by using carbon dating, with a high degree of accuracy, that is. Anyway, so let's start at the beginning. So in general, we'll express an exponential growth model according to the following. So it looks very simple. I mean, it's just e to the kt power with some initial value possibly multiplying by that e. So in other words, this y0 is a constant, and it is the initial value of y. So let's say, for example, if we're modeling bacteria growth, y0 would be the amount of bacteria initially present in your sample, and then k would represent the growth rate, which has to be non-negative. Otherwise, all of this is just a constant. There'd be no growth at all. And t is time. Okay, so k is the growth rate, t is time, that's the exponent for e, and then y0 is the initial value of whatever y happens to be. And so for any numbers that we happen to choose, like if we go back to Symbolab for a second, let's say we do have a case where we have a colony of bacteria, and initially there's 100 bacteria, and the growth rate is, I don't know, 0.0001 X, or let's call it T. It doesn't really matter if it's T or X. And let's see what that looks like. Ooh, okay, I didn't choose very well. Let's give it a larger exponent. Let's try, all right, let's see what that looks like. Let's see. That's better. Okay, that looks a lot more plausible. Okay, so you can see now, of course, if we're talking about the growth of bacteria, we could ignore what's going on in the second quadrant. We're going to say that at time 0, we start with 100, and then as time elapses, we have more and more bacteria, so that after 60, let's say, I don't know, the T could be any time frame. Let's say this is 60 minutes. We have 180 bacteria, it looks like. So it's growing pretty quickly, but not as quickly maybe as the graph we had a few minutes ago. But it is exhibiting exponential growth because the rate of the growth is accelerating as time evolves. Okay, in other words, the slope is getting steeper as we move to the right. And if I increase the exponent even more, then this effect becomes more pronounced. So let's change this to 0.1 T. And you'll see what happens. Yeah, now it's really growing. Look at that. It's just zooming along here. That's a lot of growth. Okay, so now, of course, we need to know what the growth rate is. That will come from experience or some other form of knowledge that we have. But this would be a typical example of an exponential growth model. Now, if we want to model decay, the only thing that changes is we have a negative exponent. And so let's try. Yeah, so for here, all we really have to do is change this exponent to negative, and we'll see what it looks like. All right, let's give this one a shot. Yeah, and it's falling off very quickly. So in other words, again, you'd have to, for the case of a real world example, you could ignore the second quadrant because X cannot be negative. But you can see if we start here at 100, whatever this is, this could be, for example, the amount of radioactivity in a sample of uranium, and it maybe falls off at this rate. So you can tell after 20 units of time go by how much radioactive material is left in that sample. And again, it does drop off very, very quickly. All right, now here's an example. Now this is bacteria again, 200 e to the 0.02 t, so it'll be very similar to what we were just looking at. All right, let's try that. 200 e to the positive 0.02 t. All right, let's see what that looks like. Yeah, it's growing pretty quickly. It's now, of course, the way this is written, this implies that the starting value is 200. Whatever this is, in this case, it's the bacteria. We started with 200, and you can see that the amount of bacteria is growing at an increasing rate. So it's growing pretty quickly. But suppose that we needed to know specifically how many bacteria there would be after 5 hours or 300 minutes. So let's assume that T is measured in minutes rather than hours. So that means for 5 hours, we actually have 300 minutes. We'll plug in 300 for T, and you can solve directly for this. And you can see that after 300 minutes, the colony would have 80,686 bacteria in it. I don't know if I can show that here. Let's see what we can do. Yeah, I think we can. Well, it's going to be hard to see. The 300 is in here somewhere, but it looks just about right. Those are very large numbers, of course. Now, here's another interesting we can do. What if we want to know when will the population reach 100,000? So this time we set 100,000 equal to the original function, and we solve for T. And of course, that means we're going to use natural logs. First, divide both sides by 200. So we have 500 equals e to the 0.02t. And now we take the natural log of both sides of the equation. And on the right-hand side, the log of e to some power x is just equal to log x. In other words, watch this. Okay, and so that's what we're seeing here. The exponent is now here. So we have the log. So of course, we're going to divide both sides now by 0.02. And we end up with approximately 311. So after about 311 minutes, the bacteria population will be about 100,000. Okay. And of course, in principle, you could do that with any numbers you want. If you wanted to know when they reached 1 million or whatever it is, no problem. Now, here's an interesting one because we're going to compare two different cases. We're going to have two different paintings. The first one, painting A, is worth $100,000 and the growth rate is linear. In other words, every year it gains $2,000 in value. So it's a very simple growth rate. But B is currently worth $100,000, just like A, but its growth rate is not $2,000 a year. Instead, it's growing exponentially at a rate of 2% per year. So for A, the value of the painting at any time, A of t, is very simply 100,000 plus 2,000 t, where of course 2,000 is the slope, 100,000 is the intercept. And t is years. Now, for the B though, because we were told that the growth rate is 2% per year in an exponential basis, and the initial value is $100,000, that means that this function is 100,000 e to the 0.02t. So what I've done here is I've shown what the two graphs look like on a side-by-side basis. Now, for whatever reason, I was having a lot of trouble doing this in Symbolab. So I went back to Excel, and you get a rough idea here of what's happening. The blue line is painting A whose value is growing at a linear rate. It's just a straight line. The slope never changes, but for B, the orange one, the rate of growth is actually accelerating. Okay, so in other words, as time goes by, B is worth progressively more than A. Okay, and of course, the gap between the two will continue to increase over time. Maybe the problem is that the painting B is by somebody famous like Picasso, and painting A is by somebody who's not quite as well known, so the growth is different. Now, of course, one of the reasons why this might matter to you is because if you're planning for your retirement and you are looking at the investments you have, obviously B is going to be the better choice. Now, it's not always possible to find investments like that, but as long as you understand what the growth rate looks like, that'll make things a lot easier. So like numerically, I mean, it's hard to tell from the graph, but after 15 years, at first, the two are fairly similar in price. After that, the difference starts to become more pronounced. And after 50 years, painting A is only worth $200,000. Painting B is worth about 35% more than that, about 271,000. And that will continue to grow, the difference between them as time elapses. Now, sometimes what we're interested in knowing is not what will be the future value of, let's say, a bacteria colony, but what we might want to know is what is the growth rate. So in other words, we might be given a starting value and an ending value over a specific length of time, and we want to know what the implied growth rate is. Okay, so how do we do that? So here we go. Imagine that in 2006, there were 80 deer in a wildlife population, and by 2012, the deer population had reached 180. If we know from experience that deer populations tend to grow at an exponential rate, what growth rate did they experience in this case? Okay, and that's important because then it'll help us predict what it might be in the future. Okay, and maybe we'll have to decide if it's getting too crowded or not. So N of t, it just was arbitrarily chosen number at time t. You can call this anything. But here's an important point. When you're dealing with time like this, you have to be careful with the variables. Rather than using 2006 and 2012 in our equation, we're going to designate 2006 to be year 0. Okay, in other words, time zero means today, the initial starting point. So that way, the year 2012 is defined as 6. Okay. If you try to use 2006 and 12, the results will not be correct. So what you're going to do is use 0 for the starting time and then 6 for 6 years later. And by the way, also this is important because this way the results are the same no matter what the 6 years are. Whereas if we use the actual years, that will affect the results. So here's the growth function. Now, if you notice, we did say that this is the starting value. When t equals 6, we have 180 deer in our population. So the t is 6. Okay, you can see it right here. So this means we have 180 equals 80 times e to the k6 power. And of course, k is the variable we're trying to solve for. So we rewrite it as 180 over 80. This is now e to the 6k. And of course, we're going to take log. So first we'll reduce this to 2.25. E equals e to the 6k. So we'll, of course, take the natural log of both sides. We'll have log of 2.25 equals 6k. And so log 2.25 divided by 6 is the final result. So in other words, using an exponential growth rate, the deer are growing at about 13.52% per year. So, and again, that will help us determine like if maybe we need to expand the size of the wildlife preserve, maybe we don't want the deer to get too crowded in there. So this way, at least we'll have some idea of what the population is likely to look like in the future. Now, here's one that's a lot of fun because what's happening here is that you have a very valuable collectible coin whose value is growing very quickly. So we have a silver dollar that was minted in 1899. And let's say that it is now 2019. The coin is now worth $37.42 to collectors. It's a rare coin and collectors are willing to pay that much for it. So if imagine somebody had bought this and set it aside in 1899. The question is, what kind of rate of return does that represent? So again, if we're going to assume exponential growth, here's what we have to do. We'll say V of t, value of time t, uses the same formula. The initial value was $1. The final value is 37.42, and the time between the 2 years is 120 years, from 1899 to 2019. So you've got 37.42 equals e to the 120k power. And once you've taken the natural logs, you've got log 37.42 equals 120k. And now it's just easy. You just divide both sides by 120. So according to this, if with exponential growth, the coin is growing at a rate of 6.86% per year. So if you continue to hold on to the coin and you assume that the past will repeat into the future, you can predict roughly how much it'll be worth in the future. Like if you decide to hold on to it for another 20 years, you might want to know how much do you think it'll be worth. And this would enable you to do exactly that. It also means that if you had other coins, you could compare their exponential growth rates and then compare them to each other to see which ones have done the best. Maybe you could decide, maybe it turns out that gold coins tend to increase in value more quickly than silver, or who knows. But this way you can compare them side by side. Now, here we're going to look at actual cash. We're going to calculate the future value of a sum. And what this is all about is that, of course, as you all know, when you borrow money or lend money, there's going to be interest involved. Okay, in other words, the borrower is going to repay the amount borrowed, which is called the principal, along with interest. Okay, and that's otherwise nobody would lend any money out if they weren't earning interest. So the amount of money, if you're borrowing money, the amount of money you'll pay back in the future is called the future value of the sum. Or if you're saving money, let's say you're putting money in the bank and you want to know how much your balance will be in the future, that is also known as the future value of the sum. Okay, so the future value is what a sum of money is going to be worth in the future. Now, there's a formula for this. And here's what's happening. The P is the principal. This is the amount that was either borrowed or lent. A is the future value. Now, R is the rate of interest. Now, by convention, first of all, in an algebraic formula like this, you're going to want to make sure this is expressed as a decimal, not as a percentage. Otherwise, you're going to get the wrong answer. But normally interest rates are expressed on an annual basis. Okay, now, if the interest is calculated or compounded more than once a year, let's say the bank calculates your interest every month, then N represents the so-called compounding frequency. How often are you being paid or earning this interest? Now, in the United States, mostly that will happen on a daily basis. So N would be 365. And then T is time in years. So R and T are measured in years. N is used to adjust them in case the interest is being computed or compounded more than once a year, which is normal. I mean, most of the time, the interest is compounded more than once a year. For loans, like, or money you leave in the bank, typically it's done every day, 365 days a year. So for any amount of information you're given, you can figure out the future value. And so N, by the way, N can take on a lot of different possible values. If the interest is paid twice a year or semi-annually, N would be 2. For monthly interest, 12. And then finally for daily interest, 365. You wouldn't normally see, I mean, you might see quarterly. Quarterly would just mean 4 times a year. And there might be some cases where you see this, but for the most part, you can assume that interest is compounded daily. Certainly on your credit cards or on your car loan or any other loan you may have, almost certainly it is being compounded every day. So here's a good example. Somebody borrows $10,000 for 3 years with an annual rate of 6%, but it's compounded monthly. So 12 times a year, this person is being charged not 6%, but 1/12 of that, which is 0.5%. So in other words, instead of charging you 6% every year, they charge you 0.5% per month. Now, it turns out that if you're the borrower, this is not working in your favor, because the more often the interest is calculated like this, the more you're going to pay. If, on the other hand, you're lending out your money, this makes you very happy because you'll earn even more interest. But why don't we throw these numbers into the formula and see exactly how much this person is repaying after 3 years. So the principal is 10,000. Yeah, 10,000. The rate is 6% per year. That's important. This is 3 years. And then this is 12 times per year that the interest is compounded or calculated. So we're going to plug those in. And you can see, if you take out your calculator, put this in Symbolab, you'll see that after 3 years, the borrower is going to repay $11,966.81. And of course, out of all of that, $1,966 is our total interest. And the rest is the original principal, because we borrowed $10,000. Okay. So yes, so we know that we repaid $10,000 worth of principal. The interest is $1,966.81. So the future value is the amount we actually paid back, which is $11,966.81. So here's some simple examples. We're going to take the same amount of money. We're going to have $1,000, a simple case, deposited into a 1-year bank account. The interest rate is 4% per year. And what we want to know is, how much of a difference does it make if the interest is compounded annually, which means N equals 1, semi-annually, which means n equals 2, monthly, n equals 12, and daily, n equals 365. Okay, so let's check this out. Let's throw in the numbers. And by the way, you may be disappointed to see with such a small amount of money, the difference isn't that much, but it's not something that can be ignored. So these are the three values that we start with, and in each case, n is different. So here we plug in the numbers, and of course here n is 1 because we have annual compounding. Once a year, we're credited with interest in our account. And so after a year, this is worth $1,040, and clearly $40 is the interest. Now, what happens when suddenly we increase this to twice a year, or we have semi-annual compounding? So you plug these in. So what you're actually doing here is multiplying 1,000 times 1.02 squared. And you can see this time the interest is not 40, but $40.40. So because we compounded the interest more frequently, the interest went up a little bit. Not much, like I said, 40 cents out of $40. It's not a huge difference. But if you're putting this money in the bank, that's your money. You're not ever going to say to the bank, listen, we don't want that 40 cents. You can just keep it. No, it doesn't work that way. Okay. So anyway, in the third case, when we have monthly compounding, what we're basically doing here is multiplying 1,000 by 1.00, and then you have a string of threes, and that works out to be 1040.74 rounded to dollars and cents. So now all of a sudden the interest is 40.74. And again, it's not a huge amount, but it's more than when we had semi-annual compounding, that's for sure. And so you can probably guess that with the daily case, we're going to have even more interest, but the extra amount will be not a great amount. It'll only go up by a very small amount compared to monthly. So let's find out how much it went up. Oh, here it is. Wow. You may be disappointed when you see this. But keep in mind, this is only 1 year. If you left your money in the bank for like 10 or 20 years, you'll notice that the interest will grow very quickly because of this compounding effect. So in the early years, this is not helping you a whole lot, but after enough time elapses, this starts to become very, very important. Now, here's an interesting question. And you don't see this in practice, but what if a bank suddenly said one day, you know what, we're going to offer you interest compounded every hour? The interest should go up a little bit. And then if they said, well, you know what, let's try this. Let's have interest compounded every minute. Well, it might go up a tiny bit more. And so in other words, if we keep increasing the compounding frequency, there must be some limit that we reach. And that limit is something called continuous compounding. So let me show you what this is all about. If you were to take all those results we just had, the future value and the compounding frequency n, the future value is increasing, but at a progressively decreasing rate. So there's actually an asymptote here. And that asymptote represents the case of continuous, as it's called, compounding. And what that's all about is that in the limit, this is what happens as n, the number of compounding periods per year, approaches infinity. So in other words, we're getting limits involved here. So in other words, if I keep increasing the number of compounding frequencies, periods per year in the limit, as that n goes to infinity, we reach a maximum future value, which is the result of what's called continuous compounding. And the formula for that is just simply PE to the RT. See, what happened here, we took the limit as n goes to infinity, and that's because E itself can be defined as the limit as x goes to infinity okay, so that is one way we can define E. And so we end up with this simple expression for continuous compounding. Now, in practice, banks don't continuously compound the interest rate, but it turns out a lot of financial modeling is done with continuously compounded rates because they have a lot of very convenient mathematical properties. So in our case, using the same numbers, you can see that using this formula with the same data, instead of having a future value of 1040.808, with continuous compounding, it only went up to about 81 cents. So in other words, the difference is very, very minimal. But that doesn't surprise us when we look at this graph. Imagine that, let's say, for example, this is 365. You can see we're getting awfully close to that asymptote right there. So as we keep going past that point, the change is very, very minimal. It's down here when you see the biggest changes, like from 2 to 12, that can be a very significant difference. But once we get past 12 even, the change is not very dramatic. So the continuous compounding can be thought of as the limiting case as the frequency of compounding goes to infinity. Now, here's what ties this in with what we've been doing. That means in this case, the sum of money is growing at an exponential rate R. And so if we were to plot this in Symbolab, you can look at it and say, well, the rate I'm going, how much will I have in X years in the future? So we have 1,000, and the interest rate in the numerator, the exponent, is 0.04. Let's see what this thing looks like. So by the way, I want to point out that this graph, we're plotting the future value against the compounding frequency. In the graph I'm about to create, we're plotting the sum in your account versus time. Okay, so this one's going to grow very, very quickly. Not initially. It'll take a while for the growth to really get going, like the bacteria colony. You saw how at first it grew relatively slowly, and then it starts to really take off. So we'd start here, and so you can see that after, let's say, 20 years, we got about $2,200. After 40 years, it's getting to be a huge amount of money. Look at this. You're up around 80. All right, well, here we go. 50 years, you got about $8,000, about 8 times what you started out with. So you can see that at first it grows fairly slowly, and then it starts to really grow very quickly. So this is really the secret to saving for your retirement, to start young and start saving a lot of money that you can leave in a bank account for decades, because you can see how eventually it'll start to really grow like crazy. Even if it's not being compounded continuously, even just daily will look very much like this. Okay, now we're going to do the reverse process. We're going to look at decay, and you can probably guess that it's not going to be very different. Again, it'll only be different by the sign. In other words, if you see PE, here this is exponential growth, PE to the RT. Here for decay, it's just PE to the minus RT. So that's the only difference. Growth, exponential growth, wow, I don't know what's going on here. All of a sudden, my pen is not working well. Oh my God, what is this? Okay. But yes, that's the difference between the two. So let's look at an example of this. Now we have a radioactive element that decays at a rate of 5% per day. In other words, every day 5% is converted to lead. Starting with 100 grams of this element, how much will still be radioactive after 10 days? So the decay rate is 5%, in this case per day. T is expressed in days. So therefore, we have 100 e to the minus 0.5. And so after 10 days, the original amount of 100 grams of element only has 6.0653 grams of radioactive material left. Well, of course, that's because it's decaying at a rate of 5% per day. That's why it's falling off so quickly. But this will be a classic example of how you would calculate the decay of, in this case, a radioactive element using the exponential decay function. All right, well, that's not, now here's an interesting application. What if a variable is growing exponentially? The time that it takes to double its value is log 2 over k, the exponential growth rate. Now, this can help a lot if you're trying to figure out, for example, oh, I want to double my money after X years. That doesn't look like such a complicated formula, does it? It's not. So let's look at a quick example here. We'll do something from biology. We have a population of fish growing exponentially. We start with 500 fish. And then in 6 months or half a year, there's 1,000. When will the population reach 10,000? So the population doubled after 6 months. So here's what we're going to do. Assuming the time is measured in years, k can now be thought of as your annual growth rate. So we set that equal to log 2 over k, and we can solve for k. So that implies, now that's a very big growth rate. I mean, the population is growing at 138.6% per year. So that was a big one. But with that growth rate in your hands, you can now figure out when the population will reach 10,000. And we did one just like this earlier. This is our initial value. This is the so-called terminal value. And of course, this is the annual growth rate. Okay, so you plug in the numbers, you take the log of both sides, and you'll soon discover that the time required to reach 10,000 in our fish population is about 2.161 years. Okay. So what we basically did was we started out by assuming that the population doubles from goes from 500 to 10,000. So that means we've already got values for y0 and y. We know t, actually we don't know t, we know k. It's t that we're looking for. And so here we end up with about 2.161 years. And you can use something like this too to ask yourself, well, how long will it be before my investments are worth X dollars and I can retire? That might be nice if you can sit down and figure out how long should it be before I can retire given the investments that I have. That's something that financial planners can do and often do on a regular basis. Now, how about this one, half-life? So we're thinking now in terms of exponential decay. So this formula is also going to be used now to figure out how long it takes to cut the value in half. Now, K is the decay rate in this example. So let's say that the half-life of the isotope carbon-14. You might remember from high school that carbon actually has an atomic weight of 12, but when it takes on 2 more neutrons, it becomes carbon-14. And so we call it an isotope. And so it's 5730 years, which means that it takes that many years for half the carbon-14 in a substance to revert to the non-radioactive isotope nitrogen-14. And we also know that carbon-14 decays at an exponential rate. This is why they're able to use this stuff so accurately, because they have all this information. So if they find a new mummy in Egypt, for example, it's not that hard for them to figure out how old it is. And of course, you've probably seen this used on crime shows like Law and Order. Like if somebody finds evidence, it can be determined if it's old enough to have been used in the crime. And more recently, a lot of technology has advanced in the field of determining or identifying art fraud. In fact, I went to an interesting exhibition a few years ago, and they had some paintings there that were forgeries. And the way the forger was caught is not because somebody could tell by looking at the painting that it didn't look right, but what happened was some of the paints that were used were proven by this technology to not be old enough to have been painted by that painter. And so this is exactly the kind of thing that can be used to trip up art forgers, because you can say, well, look at these paints. This painting was supposed to be done 100 years ago, but these reds are only 50 years old. So that means something's wrong. It's a very interesting area. So in other words, it's getting harder and harder for this type of crime to be committed. So we set the half-life to 5732 log 2 over K. So the K, as you can see, it's a very slow decay rate, 0.000121. And so now what this means then is that now that we have K, we can predict how much will be left after any number of years. Okay, so in other words, this time we have the time and we have the decay rate. And so that leaves us with the amount of radioactive carbon-14 after 50 years, about 99.4 grams. Now, here's where, this is where you can use this for a Law and Order episode. Whatever it is that we're looking at, we know that originally contained 100 grams of carbon-14, and now it's down to 10. What is the implied age of the artifact? Okay. Well, now, by the way, we're assuming that this is the same decay rate for carbon-14 that we had here. So we plug that in. We have this new value, which is 10. The original value is 100. So doing all the algebra, we end up with 19,030 years. Okay, so this is clearly something from, prehistoric times. Maybe it's a mastodon's tusk or something like that. But at least now we have a pretty good idea of how old it is. Okay, and that will help us determine if it's valid or not. There's a lot of applications we can use here. And this kind of thing is also done with documents. Like if somebody's trying to sell a supposed copy of the Declaration of Independence, this kind of technology can be used to determine how old the paper is, and the ink as well, and find out if this is for real or not. But like I was saying, it's especially useful now in the area of detecting art fraud, because one of the hardest things for the forger is to make sure that materials have the right age. Some of these forgers can copy anything. It's unbelievable if you've seen some of these documentaries, but this is what trips them up. The fact that they have to have a canvas that's the right age, the paints have to be the right age. And if not, it'll be clear right away that there's a problem. It's the same thing can be used for wines, as it turns out. If somebody claims that they have a bottle that was, a bottle of wine that was from the 19th century, it's not hard to tell with this technology how old the bottle really is. Okay, so it's very interesting. I'm sure there's many other applications that we can think of. So, but all of this basically represents some of the many exciting applications that we can come up with from exponential growth and exponential decay. So you never know what this math can be used for. I found these to be particularly interesting examples. Now, the rest of this chapter has other examples as well of applications of derivatives, but for the most part, they're really more physics related. So I'm saving those for a separate discussion. And for example, we can use them to calculate areas and volumes, and not just simple shapes, but like cylinders and things like that. And it gets a little into the area of geometry, but for now, we'll just leave it here. And soon enough, we'll have the rest of this material, and then we can start thinking about a final exam at some point. So um, I'll stop right here and I'll see you soon.